Dear students, you have now seen the single layer perceptron and multi-layer perceptron basic details. In today's class, you are going to see about fully connected network. Okay, so what exactly is a fully connected network? The other name of fully connected network is a dense layer. Alright, so dense layer or a fully connected layer is actually the basic building block of a neural network. It is characterized by each neuron in the layer being connected to every neuron in the previous layer, thus forming a fully connected network structure. So I can say that fully connected network has actually evolved from a multi-layer perceptron, and inside that, in a layer, whatever number of neurons are present, whatever number of perceptrons, when I am talking neuron, it means a single perceptron. So whatever number of neurons that are present in a layer, they are all connected to every other neuron present in the previous layer. So when you have that full connections of these neurons, you create a dense layer, which we call it as a fully connected layer, right? So what are the basic things that a fully connected layer consists of, we are going to see. So the very first thing that it is going to consist of is an input. Okay, so each neuron in a fully connected layer receive input from every neuron in a previous layer. So for an example, you have seen the multi-layer perceptron, right? You have input layer, you have hidden layer and an output layer. Then you have got neurons present here, correct? So when suppose this is your layer, and when each neuron in a fully connected layer receives input from every neuron in the previous layer. So every neuron in the previous layer, if this is the previous layer, then it should be connected in this way. It should be connected to every other neuron in the next layer, even this one. And this one should be connected to every neuron in its previous layer. So when you form a connection like that, then it is called as a fully connected layer. So input layer, if the previous layer, suppose if this is your previous layer and if this is your input layer, then what it will have then? There is no connection to this side, there is no connection. Then what it should have? It should be having whatever data that you are supplying. So input layer, if it will be having input as your data or features of your data that we call, speciality of your data. What are the features of your data that you are giving to the model to train? So if it is an input layer, the previous part of it will always be features of data. Apart from input layer, whatever other layers are there, you will be having the previous neurons fully interconnected to that. So that's how gives you the structure of a dense layer. Now the second thing that is going to present apart from the input are the weights. So whatever is the connection between these first layer neuron to second layer neuron, they always have a weight associated with it. You always prioritize these connections using weights. So every connection between the neuron in the previous layer and the next layer is associated with a weight. So what does this weight determine? This weight will determine the priority. This weight is going to determine what is the strength of this particular connection for this neuron to that neuron. And all these weights have to be updated, they have to be adjusted during the training process so that learning can happen. You initialize the weights on your own, but you cannot say whatever you have initialized is correct. Okay, whatever connection you thought is strong is actually correct. It can give you a correct output, it may not. So if it is not giving you, then it's your duty to update this weights. So that's all is the entire story of single layer perceptron or multi-layer perceptron, or if there is full connection between these neurons, fully connected layer. Okay, whatever it is, the entire foundation story remains the same. You initialize some weights and bias, which are nothing but the parameters. You just try to find out the predicted output. You compare it with the actual output. You try to learn. If there is error, please go back, readjust your strengths, readjust your parameters of weights and bias, and then you keep on readjusting till you get your correct output. Okay, so that was your constituents of a fully connected layer. The first one is an input, the second one is a weight, and then the third one is a bias. So I already told you each neuron in a fully connected layer also has a bias which is associated with it. So what is this bias term? the bias actually adds to the flexibility to the output. So, the bias term provides the neuron with additional flexibility to learn to the desired output. Okay. So, using these weights and bias, these two are the basic parameters that you try to update in order to optimize the particular model in whatever model it is. Okay. So, these are the three constituents. Apart from that, what is it? You are having a weighted sum every single time. So, you passed on to the weights to your neurons, you passed on the biases to the neurons, you passed on the inputs to these neurons. Now what next? You have to find out the weighted sum. So, for each neuron in a fully connected layer, suppose this is layer 1, this is layer 2, and you have got, there can be 3 also in this, and suppose this is layer 3 for an example. It should be connected to every single neuron, then only it is a fully connected layer, and here it could be input features. Okay, so this is a fully connected model, right. So, now what is happening? The inputs from the previous layers, they also have their weights. So, these inputs should be multiplied with their weights, and then you have to add them together, and while adding you should also give the biases. Okay. So, once you get that, after that you have to pass it through an activation function. So, the weighted sum computed for each neuron will be then passed through an activation function. What is the purpose of activation function? Because I told you, why are we using a multi-layer perceptron? Fully connected layer is actually a type of multi-layer perceptron model only, right. But why are we choosing that multi-layer perceptron model? Why are we choosing this dense layer or a fully connected layer? Because you want the model to be capable to solve non-linear problems also. So, how do I now introduce non-linearity into this network? By using suitable mathematical logic, which is given as an activation function. So, this activation function is responsible for your model to perform even non-linear problems, to perform on non-linear planes, non-linear problems also. So, activation function basically introduces non-linearity into this particular network. So, what are the various activation function, what roles they play, we will have a separate session on it. But right now you understand activation function imparts non-linearity to your model. Okay. What are the various activation functions that you could use? There are many like sigmoid, tanh, ReLU, softmax. What are all these? Why they are used? Separate session on it. Okay. Then we have got output, final thing. So, the output of each neuron in a fully connected layer is the result of applying activation function to the weighted sum that you have got. So, all these constituents together they form a dense layer. So, you can see here as a very simplest fully connected layer I have presented here. Suppose you have got 3 neurons, x1, x2, x3 are the inputs to it. The weights are W11. Now what is this W11 and W12? This is the first neuron and this is the first output. Okay. This is the second output O2 that I am referring. So, I write this as W11, I write this as W12. So, this represent the current layer and this subscript represents next layer where it is connecting to. Okay. So, this one represents the first neuron in the current layer, this one represents the first neuron in the next layer. So, 1, 2 will be the first neuron in this layer, second neuron where it is connecting to in the next layer. So, that is how strategically you will write down the weights. There is always a convention that you write the weights as. So, similarly, how about this weight? This will be W21 because this is the second neuron in my current layer and it is connecting to the first neuron in my next layer. And for this I will be writing W22 and for this I will be writing W31 and for this I will be writing W32. So, you have to move as per convention only. Okay, the first subscript current layer neuron where it is connecting to in the next layer should be your next subscript. So that's how a simplest fully connected layer can be designed. So what are you going to do? First, you are going to take the product of weights W11. Suppose I want to calculate only O1. So where is O1 coming as? 1 second. So where is O1? Suppose I want to calculate O1. Where is O1 coming as? O1 has got inputs as from X1, from X2 and X3. What are the weights? W11, W21, W31. So what I am going to do now? X1 input multiplied with W11, X2 input multiplied with W21, X3 input multiplied with W31. This is what I did, and then I have to add them. The first half of the activation function is addition. So you add them to create a linear model. You know, adding together creates a linear model, but you want to impart non-linearity to this model. So the second half is always activation function, which is represented here as sigmoid function. So what does the sigmoid function will do? The sigmoid function is going to work. This is the non-linearity that is actually provided. So what I am going to do here is, I am going to give it like this. So this is 0 and this is 1. So any positive value of this particular weighted sum will give the output as 1. Any negative value of this weighted sum will give the output as 0. And same thing goes with O1. Okay. So O1 and O2 you are going to do. So if I want to express the entire network relationship as a matrix, then what I am going to do? As a matrix I am going to write O1, O2. X1, X2, X3 are the inputs, and you can see here I am using @. This is the vector of weights, this is the vector of bias. If I want to represent it in matrix form, I am going to write it as O is equal to, you can see I am using all capital letters, X plus B. B is still a vector, not a matrix. Okay. So X is a matrix, W is a matrix, and B is a vector here, and @ represent matrix multiplication. So this is how is a representation of a fully connected layer mathematically. So what is the shape of the input matrix? Shape of the input matrix is going to be B comma D in. So B, that is the number of the samples, and D in, that is the number of input nodes. What is the shape of weight matrix? D in comma D out. Okay. D in is the number of input nodes, D out is the number of output nodes. Okay. And what is the output matrix? The output matrix consists of the output of B samples, and what is the shape of output matrix? It is B comma D out. Okay. So this was about mathematical representation of a fully connected layer. I hope you have got it. So you have to make sure how it is derived, you have to make sure how the dimensions are. Once you are clear with this, then you can build different types of neural network models based on the similar concept.